In this video, we're going to talk about graphing rational functions. So we're going to first talk about all the major features of the graph and how to find them. So a rational function is a function of the form where you would have a polynomial divided by another polynomial. So for example, I might have r of x is equal to x plus 1 times x minus 1 over x plus 1 times x minus 5. That's an example of a rational function because it's a polynomial divided by another polynomial. And in this particular case, I have it in factored form. Now, the domain of a rational function is going to be all the values that we can plug in except for the values that cause us to get 0 in the denominator. So if you think back to section 3.1 and 3.2 when we talk about finding domains, there's two restrictions. We have to worry about negative numbers under even roots and zeros in the denominator. With rational functions, we don't have to worry about radicals. We just have to worry about denominators. The domain in this example, if I use set builder notation, it would look like this. All x such that vertical line there means such that all x that are not equal to -1 or 5. Now I say -1 and 5 is because that is what would cause me to get a 0 in the denominator here. So now let's go on to holes in the graph. This is one of the major features of a rational function, but this doesn't happen for all rational functions. This only happens sometimes. And you might hear it called a removable discontinuity as well, which is why I added that into the notes in parentheses. So we have a hole in the graph when you have a factor in common in the denominator and in the numerator. So if you have a factor in common and you go to simplify that rational function by dividing x plus 1 over x plus 1, what's going to happen is you can divide the x plus 1 over x plus 1 for all values of x that are not equal to -1 because you can't divide by 0. So here's our common factor that we would divide out, but we still can't have x is equal to -1. So the whole would occur at the value of x that makes the common factor zero. And in the example that I have above, that would be x is equal to -1.
Graduate work in areas such as abnormal psychology and sociology, as well as
Okay, so for X-Intercepts, if you recall, the X-Intercept is the value of x when y is equal to 0. So what you want to do is when you're finding the X-intercepts of a rational function, you want to set that rational function equal to 0. And let me add in here that this is after simplification. Okay, so I would set this rational function equal to 0 after simplification. So in this example that we're using from above, I would have x minus 1 over x minus 5. Now, for an entire fraction to be equivalent to 0, the top would need to be 0. So, for example, if I had 0 over 5, that's equal to 0. Or 0 over negative 100, that's equal to 0. So as long as the bottom number isn't 0, if it's just the top number that's 0, and you just have 0 over some number, the entire fraction is 0. So if I'm looking for the x-intercept, and I set that fraction equal to 0, the x-intercept is going to happen wherever the top is equal to 0. So in this case, if I set the top equal to 0, that's going to be x is equal to 1 as our x-intercept. And if we write it as an ordered pair, it would look like that, 1, 0, because it's the value of x when y is 0. So in general, after you simplify, it's whatever makes the top 0. Okay, for the y-intercept, that's the value of y when x is equal to 0. And again, this is after simplification. Okay, so I have y is equal to x minus 1 over x minus 5, but then we plug in 0 for x. So I have y is equal to 0 minus 1 over 0 minus 5. So I would get 1/5 as my y-intercept. And if we write it as an ordered pair, it would be 0, 1/5, because it's the value of y when x is 0. Now, horizontal asymptotes is another major feature of the graph. And a lot of times we have horizontal asymptotes. And a horizontal asymptote is where we're trying to find the value of y when x goes really far out into the large positive numbers towards positive infinity, and as x goes way, way far out into or by in the direction of negative infinity. So we want to see basically what y value are we getting closer and closer to as we go way far out to the right and to the left. Now, there's ways to do this algebraically, but in my opinion, I think it's easier just to know the rules. Because when you get into calculus, if you have to go on to calculus, you're going to go back and revisit this and definitely do it algebraically when you're dealing with something called limits. So let's just go by the rules. And there are 3 rules, and they're more of situations that you want to look at. And what you're going to do is you're going to figure out which situation you fall under and then follow that rule. So the first situation is if the degree of the top is equal to the degree of the bottom, then what you're going to do to find the horizontal asymptote, it's going to be y is equal to, and then you have the leading coefficient, I'm going to abbreviate LC, the leading coefficient of the top polynomial divided by the leading coefficient of the bottom polynomial. The second situation is if the degree of the top is smaller than the degree of the bottom. then your horizontal asymptote is just going to be y is equal to 0. And the last possible scenario is if the degree of the top is larger than the degree of the bottom, then there is no horizontal asymptote, and I'm going to abbreviate HA for horizontal asymptote. And in fact, if the degree of the top is only 1 bigger than the bottom, so for example, if the degree of the top is 4 and the bottom is 3, there's something actually called, instead of a horizontal asymptote, a slant asymptote, but we're not going to really get into that in this class. Okay, last major feature is vertical asymptotes. Vertical asymptote is when you're looking for the value of x when your vertical value is shooting up to negative or positive infinity. Or shooting down, I should say, to negative infinity, or shooting up to positive infinity. So that's when we're looking for the x value. So for vertical asymptotes, all you're going to do is, after simplification, you're going to look to see what makes the denominator 0. So those are all the big features of the graph that we're going to be looking for, so that we can put those all together and actually draw the function.